All right, thank you for coming back. This is the stuff from the textbook. So I need you on page 47 in the Springboard textbook so we can get moving on this. And this is basically getting you to write, graph, analyze, and model with exponential functions and solve exponential equations. Now, this is going to bleed into lesson 4.4, which is great. But for right now, we're just going to kind of take what we learned from our last packet and apply it here. Fun fact, Harry Casey was the first winner of the Pennsylvania lottery, and he won $1 million, and he retired. He got 20 annual installments of $50,000. So he retired. He spent $50,000 each year, and by the end of the 20 years, he had no money and was broke after winning $1 million. So Margaret wants to do it a little differently. She wants to save her first lottery payment and deposit it so this can grow. And then she'll take her next payment and maybe spend that. So the first thing we need to do is take a look at the years going through. This happened, it looks like, in 2004. So Margaret won in 2004. And then every year after, we're looking at how the interest is building. Okay. So because we're in the exponential function unit, one of the things that we talked about on the previous packet was we recognize this is growth because the money's getting bigger. So we're going to divide the next one by the previous one. So we're going to take 52,500 and divide by 50,000 and see what you get. And we have a growth factor of 1.05. Then we're going to take 55,125. And we're going to divide that by 52,500. And you get 1.05. So it's consistently increasing. And this is our growth factor. Remember, it's above 1, so this is growth. How much above 1 is it? 0.05. So that means that there's like a 5% increase. I can tell because this right here tells us what the increase is. So the 0.05 is a 5% increase. Remember, the 1 just tells us it's growth. So to make this go super faster than multiplying everything by 1.05, what we're going to do is we are going to go ahead and fill this part in because this part's easy. So 0, 1, 2. In 2007, it would be 3. 2008, it would be 4. 2009, it would be 5. And then there's a jump of 5 years, so that would be 10 years later. All right. Now, what we can do to calculate these values so much faster is using the fact that this is a growth model. And we know that we started with 50,000, so that's super important that we recognize 50,000 is our beginning. And we are increasing by 5%, so 1.05. And we're looking after the third year, so our exponent is going to be 3. So I have my calculator here on this side because you know I can't do this in my head. And I am literally typing in exactly what we see here. And I got $57,881.25. We're going to do the same thing, except we're going to, I might just change my pen color so you can trace it easier. 50,000, 1.05, and we're going to raise that to the 4th power because we want to see what's going to happen 4 years after. And she's already got, who was this? Margaret. She's already got this up to $60,775.31. So she didn't touch this money. She's just letting it grow in the bank. So 4 years after she put it in, she's already over 10 grand in free money. It's just letting it sit there. We're going 5 years. 50,000 after 5 years at 5% interest growth. And we're at 63,814.08. And lastly, we got one more to go. I'll go back to blue. 10 whole years later. She didn't touch it for 10 years. What kind of money does she have? 10 years later. Oops, I made a mistake. I put 2 decimals by mistake. Oh, she's up to $81,444.73. Boom. This to this is insanity. So you put $50,000 in the bank, don't touch it for 10 years, and it grew $31,000. That's a nice nest egg. That's what she wanted. She wants her money to build and grow so that she has something when she's done getting her payments. So what are some patterns we notice? Well, this is a growth pattern, and it is increasing by 5%. It is exponential. This is what you call that steep up. Okay, it's not linear. This starts looking linear. Look, 2,000, 3,000, 3,000, 3,000, 3,000. And then all of a sudden, if you go up 10, it's like, whoop, it's way up there. Okay? So that's kind of like the premise of what this whole thing is about. What do we need to know? This is a key and crucial, important piece of information. You need to highlight this, and you need to know this. The general form of an exponential function can be expressed as f of x equals a times b to the x. We're going to talk about that. F of x equals a times b to the x. We're going to use this formula to write exponential equations from points. Okay? This is my y. This is my x. This is my initial. Now, this cannot be 0 because you can't begin with nothing and have it grow. Nothing does not grow. You have to start with something. Okay? So when it says that a is a non-zero constant, a has to be a value that you can start with. Okay? B is a positive constant. B has to be positive. This is our growth factor. Can also be decay factor. You know, like whether it's growth or decay, that's what the B stands for. That's the growth factor, or the amount that's increasing or decreasing. But it cannot be negative. It is positive. And it cannot be 1. And I'll tell you why. Because if I take 1 to the 6th power, it doesn't change. If I take 1 to the 20th power, it doesn't change. In order for it to be growth, it has to be greater than 1. In order for it to be decay, it has to be less than 1. But it cannot be equal to 1. Okay? So growth is going to be larger than 1. Decay is going to be less than 1. But it cannot be just 1. Okay? So that is like key and crucial stuff here. Why is exponential function appropriate for the data? Because it's got a constant growth factor, but a constant multiplier. We took the last and divided by the previous one, took that one, divided by the previous one. We got a constant multiplier of 1.05. This is why exponential functions exist, because they have a constant multiplier that brings us to the next value. What is the constant multiplier? Oh, we just did that. The constant multiplier is 1.05. And how do you find it? You've got to take the next and divide by the previous, and this is y values. Oh, O-U-S. You take the next one and, hold on. Hello. You take the next one, divide by the previous one. Take the next one, divide by the previous one. You divide upwards of your y values. Okay? So that's this page. 47 is done. Moving on. All right, so we kind of already did this. We talked about the growth factor. I don't really want to spend time going over this because it's just looking for the change in values and the fact that the money change is not going to be constant. It's not linear, but the growth factor stays 1.05. Okay, the growth factor is going to stay 1.05 because that's the definition of an exponential. These are going to change because as the thing gets bigger, it's going to expand more between. Now, this is what we're looking at. We're looking at Margaret's money in the account after 10 years. So, let me pull this apart. We're going to plot this. So at 0, we were at 50,000. That's here. At 5, we were at 63,000. So, and yes, we have 1, 2, 3, 4, but I was just looking to make it go faster. And then at 10 years down the line, we're at 81. So this is not linear. You can see it start to swoop. Okay, we got the money in Margaret's account after 10 years. We did 50,000 times 1.05 to the 10th power, and we ended up with 81,444.73. This was on the previous page. We did it right on Model 1's table. Now, how many years are needed to double her investment? Well, that's an interesting question because in order to double her investment, she would need 100,000. So 10 is not enough. We have to keep moving and we have to keep figuring out. So we're going to do a little estimate. 10 gives you 81. Do you think we should try 11? Do you think we should try 12? What do you think? I'm a little leery to go up too high because 81 was a big jump. So maybe we'll try 12. Let's try 12. 50,000 at 1.05, and we're going 12 years in. We're going to see what happens. We're going to see what Margaret's going to get. 50,000, 1.05. We're going to go up to 12. And 12 only gives us, not only, but 89,792.82. All right, so that's still low. Okay, maybe a little bit higher, so maybe 15. Let's try 15. Now, this is strictly estimating. I'm trying to figure out how to get to 100,000. To double her investment, she needs twice 50,000. That's $100,000 is what we're looking for. So I'm trying to figure out how many years it's going to take to get me to 100,000. So I'm just trying different years. This was a little low, so I'm going a little higher now. Oh, okay. This is 103,946.41. All right, so this is a little over. Let's see what 14 does. If 14 is too low, I'm not sure. We're going to give it a shot. All right, so we're just going to go do this, but we're going to put 14 in and up. Okay, so 14 years is $98,996.58. So how many years is going to be needed to double her investment? Well, after 14 years, she doesn't make it. It's not enough. So in order for her to double her investment, she's going to need a total of 15 years to reach 100,000. Now, she's going to get a little bit more than that. Like I said, the amount that she's going to get is going to be 103,000. But 15 years, that's what it's going to take to reach $100,000. Okay. So let's go to 15 and plot that. And there you go. Nice little curve. It's not linear. Not linear. Okay. So we used our equation from item 6. Oh, yes, I guess we missed that. We wrote the equation back then. So this is A of t. This is saying the amount of time or the amount of money after time has passed. We're going to start with 50,000, and we went 1.05 to the t power, where t is the number of years. So this is the formula that we've been using since page 47. This is what we use to figure out what would 12 years be, what would 15 years be, what would 14 years be. And we figured out it would take 15 years to double. Okay, so what I would like is, I would like for us to take a look at, this is page 49. And what we are going to do, I think, is I'm going to leave this one for our homework. So 49, we're going to leave as homework. And we're going to take a look at 9 and 10. Okay, we'll do 9 and 10. And give those a shot, and then contact your teacher with questions.